I'll be giving an introduction to Le Chatelier's principle in this video. When a reaction is at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. In this case, the rate of hydrogen and iodine gas forming hydroiodic acid is the same as the rate of hydroiodic acid turning back into hydrogen and iodine gas. I like to imagine that the reaction is in some sort of perfect harmony because it goes back and forth at the same rate. Le Chatelier's principle is similar to the idea of a balanced scale. When this scale is balanced, it doesn't tilt a certain direction because the weights on both sides are equal. Similarly, when a reaction is at equilibrium, it doesn't shift a certain direction because the rates on both sides are equal. Take a look at how the conditions for equilibrium parallel that of the conditions of a balanced scale. I like to think of equilibrium as being in this balanced state. But in a Le Chatelier's principle problem, we usually disrupt this balance. So let's imagine that we have this balanced scale. What happens if I add more weight to the right side of the scale? Well, the scale would no longer be balanced because one side would be heavier than the other. So a change has to happen. This change comes when the scale tips towards the right. What I'm trying to show you is that there are changes that happen if we disrupt this balance. Now let's parallel this to chemistry. What happens if I add more substance on the product side of the reaction? You may be thinking that if we add more products, our reaction will end up looking like this, that it will end up having unbalanced rates. But in chemistry, our reaction always tries to return back to equilibrium. So our reaction will try to return back to this balanced state. So how do we get from here back to here? The answer is simple. We turn our products into reactants. We do that through the reverse reaction. Through the reverse reaction, we can re-establish a balance. After the reaction has reversed back enough, we're going to have new equilibrium amounts that reflect the amount of products we added. I'm going to summarize what just happened with this graph. Our reaction was initially at equilibrium before we added the extra product at, say, 5 seconds. The amount of reactants and products levels out just before 5 seconds, which indicates that we're at equilibrium. Now, when we add that extra product, the amount of products we have immediately increases. As time passes, our reaction tries to get back into equilibrium through the reverse reaction. This is why we see the amount of products go down and why the amount of reactants go up. As time passes, we eventually re-establish a new equilibrium, as you can see at 10 seconds. This new equilibrium we have will contain different values than our initial equilibrium because it reflects the extra amount of product we added. So notice the new equilibrium value for hydrogen gas is higher than the old equilibrium value, and that is because of this addition of hydroiodic acid. And that's essentially Le Chatelier's principle. It states that when I add or remove something in a balanced reaction, then the reaction will either go forwards, backwards, or stay the same in response to that change. In this case, our reaction moved backwards. You will mostly see either temperature, concentration, or pressure being modified. We're going to be taking a look at each of these instances. First, let's take a look at concentration changes. This is the type of change that we just looked at earlier. Concentration changes only apply to aqueous solutions or to gases, so any changes to solids and liquids will be ignored. This one is quite simple. If I add a product or something that forms a product, then my reaction is going to shift towards the reactants or to the left. If I remove or decrease that product, then my reaction will shift towards the product side or to the right. On the other hand, if I add a reactant or something that dissolves to make a reactant, then my reaction will shift towards the products or to the right side. And if I remove or decrease that reactant, then my reaction will shift towards the reactant side or to the left side. So these rules are general and they don't apply to just this specific problem, but to just about any concentration problem dealing with Le Chatelier's principle. So make sure you understand these 4 rules and know which way a reaction shifts if you change the amount of reactants or products. Using this information, which way do you think our reaction will shift if I add in some sodium fluoride? To answer this question, we have to recognize that sodium fluoride dissolves into sodium and fluoride ions. We don't really care about the sodium ions because it's not part of this reaction. However, we pay attention to the fluoride ions because that is part of the reaction. When we add sodium fluoride, it dissolves and we end up increasing the amount of fluoride ions we have. Fluoride ions in this reaction is a product, and if we increase the amount of product of an aqueous or gaseous substance, then our reaction will shift to the left. Now let's talk about pressure or volume changes. I want you to understand that pressure and volume deal with only gases. So in this image here, I have two containers. They both have the same amount of molecules inside of them, but one container is smaller than the other. I want you to understand that decreasing the volume of a container means that the gas has less free space to move in. As a result, the gas molecules will hit the side of the container more often, which increases the pressure. On the other hand, if we increase the volume, then the pressure will decrease because the gas will have more free space to move around in, and therefore hit the sides of the containers less often. So here's a summary of what I just said. The thing about these types of problems is that volume and pressure affect both sides of the reaction, since both reactants and products are inside the container. This is different than what we saw earlier, where we only added or removed from one side of the reaction. The way you determine which way a reaction shifts is by determining which side of the reaction experiences a greater magnitude of change. Let's take this question as an example. We're trying to figure out which direction the reaction shifts if we decrease volume. If we decrease volume, then we're going to increase pressure. The first step to answering this question is to count up the total amount of gaseous moles on each side of the reaction. And you do this by adding up the coefficients of your gases on both sides. When we do that, we'll see that our reactants have a total of 4 moles of gas, while our products have a total of 2 moles of gas. If pressure is increased on both sides, the reactants will be more affected because there are more reactants than products. In order to compensate for this increased stress on the reactant side, the reaction will shift to the right. If you're having trouble visualizing this, then we can bring back the balance scale. When we decrease volume, we cause more stress on the reactant side than the product side, because the increase in pressure affects the reactant side more than the product side. In order for our reaction to decrease this stress and rebalance itself, it must turn some of that reactant into product. As it does that, as it turns this reactant into product, it becomes rebalanced. Now, what would happen if we increased volume? You're probably thinking that the opposite would happen, which is true, but I'll still go over the thinking process. Like in the previous problem, we start by finding the total amount of moles of gas on both sides of the reaction, which we've already done. Now, if we increase the volume, we're decreasing the pressure on both sides. 4 moles of gas will be more affected by this decrease in pressure than 2 moles of gas because it's a bigger number. To compensate for this greater decrease in pressure on the reactant side, the reaction must shift to the left. We can again bring the balance scale back. The amount of pressure we lose is greater on the reactant side than the product side because of the coefficients of the reaction. To restore this balance, we must turn some of the product back into reactants, and we do that by shifting the reaction to the left. Here is a summary of how to deal with pressure or volume changes in a Le Chatelier's principal problem. Remember, only count the moles of gas. You must ignore any other state of matter. Now, I didn't mention inert gases before, but what it means is that if I were to add a gas that's not part of the reaction, there would be no shift in my reaction. For example, if I added neon gas into this reaction, there would be no shift because neon gas is not part of the reaction. And this does seem like common sense, but the College Board will try to sneak in this type of concept, so make sure you know that adding inert gases have no effect. We're going to discuss the final change, which is temperature. The good news is that changes in temperature are very similar to changes in concentration. So as long as you understood the concentration parts, this part should be really easy. The key behind solving this type of problem is to remember about endothermic and exothermic reactions. Exothermic reactions release heat, while endothermic reactions require heat. To solve these types of problems, we must think of heat as either a reactant or as a product. I'll show you an example. Before we even look at this question, let's look at the reaction. This reaction has a negative delta H value, meaning that it is exothermic. Because heat is being released in this reaction, we can think of heat as a product. Now let's take a look at this question. Which way will this reaction shift if the temperature is increased? If I raise the temperature, then what I'm essentially doing is that I'm increasing the amount of heat, which is a product. Now, on my earlier slide about the general rules of concentration changes, do you remember which way a reaction shifts if we increase the amount of product? Hopefully, you said to the left or to the reactant side. We would see the opposite happen if the temperature was decreased, because that would mean less products. For practice, you can pause and try to solve this problem on your own. So, good luck! To solve this, we must first take a look at the delta H values in order to determine if the reaction is endothermic or exothermic. Because it's a positive value, the reaction is endothermic. This means that heat will be a reactant because heat will be required for this reaction to happen. Now let's take a look at the question. Which way would this reaction shift if temperature is decreased? If we decrease the temperature, then we're going to decrease the amount of reactants. Hopefully you remember that a decrease in the amount of reactants results in the reaction shifting to the left. In general, these are the two rules that you have to follow when predicting which way a reaction will shift after a change in temperature. Don't worry about the states of matter or anything, because you're just looking at the heat. That's all. Here's a summary of everything I said, so thanks for sticking with me and goodbye.